your general formula for any thing is ax to the power n integrated equals ax to the power n plus 1 all over n plus 1. Like so. So if we take any old function, we will say 3x squared plus 1/2 x plus 4. We now write it showing that we're going to integrate like this. That doesn't look like a square, now does. 1/2 x plus 4. And this just means with regards to x. We're doing it to things that involve x. So if we apply now, we've now applied this to each of our separate terms. So 3x squared, you take 2 plus 1, 3x, 2 plus 1 is 3, all over 2 plus 1, 3. Plus 1/2, this is obviously just x to the power 1, to add 2 to that we get squared. So we get 1/2 x squared all over 2, and again plus 4, that's x to the power 0, so bring that up, x to the power 1, that becomes x, so we get 4x over 1, so that's just 4x. We just tidy this up quickly. Tidy this up quickly so we get x cubed plus 1/4, I believe, x squared plus 4x. And that is your integrated thing. You apply this to each of your separate terms in turn, and that is there. That's it. Done. Okay. As you know, one use of integration is to find your original equation from a differentiated function. The problem with this is that when you differentiate, your constants, your original constants are lost because you have times them by 0. So when you do a general formula for integration, you have to remember to add a c, an unknown constant, on afterwards. However, if you have a known point on the curve, which is over here.
No.
If you have a known point on the curve, however, if you have a known point on the curve, you can plug this in to find your constant, and it's all fine and dandy.
Particular equation.
This is the particular equation.
Nice.
So to integrate an area bounded by A, B, and your x-axis is as follows. This is the general formula for doing this here. So we're going to put our numbers in as follows, like this. So we've got 3, 0, your function, which is 3 plus 2, the other way around, sorry, minus x squared plus 2x plus 3 with respect to dx. Like that equals your area. And now we're going to apply your integration thing which we talked about earlier. So we're going to change this into its integrated form, I guess what you call it, which is minus 1/3 x cubed plus x squared. Earlier in the video we're going to show how to do this, so you should already know. Plus 3x. That is it there. So to actually find your area, you do this first with your b, which is 3, and your a, which is 0, like this. What should I do? I'll do it over here. So we have minus 1/3. I'm going to get it right, aren't I? 3 cubed plus 3 squared plus 3, which equals minus 9 plus 9 plus 9, which equals 9. And then you do it with 0. So, obviously, 0 is going to be minus 1/3, 0 cubed plus 0 squared plus 3, 0, which obviously equals 0. So, if you then take 9 minus 0, and that equals 9. So the area of this curve here is 9 units squared. And then obviously that's simple because your A in this case was 0. But if your A is anything except 0, you take your result of B, your result of A, minus them as I've done here, you get your result. And that's how you integrate given B, A, and your x-axis.
When finding the area under a curve, if you draw trapeziums underneath the curve, it will give you a rough area. But as you can see, you're missing out parts of the area. If you make the trapeziums thinner, you're removing part of that error. So what integration does is split the area under the curve into an infinite number of trapeziums, so you get a precise value for the area underneath. Sometimes you can't. When you can't integrate a curve, you can use the Trapezium Rule to approximate the area underneath it. You split it into trapeziums of length h between the points A and B, and then this is the formula you would put your values into.